this. Okay, Bismillahirrahmanirrahim. So last time we looked at the reactions to produce an acyl chloride. Okay, so an acyl chloride is a new functional group that you have met. It consists of a carbonyl, C double bond O, an alkyl group attached to it, and also a chloride. Okay. There are three reagents that you can use: Socyl-2, SOCl2, PCl3, and PCl5. Okay, and as you can see, Socyl-2 does not require special conditions, so as PCl5. PCl3 is the only reagent that needs heating. Okay, so if you can choose, if you are given an option, choose the reagent that doesn't require any special condition. Okay, just check your answer here. As I said earlier on, if you want to prepare the propanoyl chloride, obviously you need a propanoic acid. Okay, so propanoic acid reacting with SOCl2 to form a propanoyl chloride and other products. Okay, methanol chloride, you need a methanoic acid, and a PCl3. You need to heat it. Okay, so you will form a methanoyl chloride and a phosphorus acid. So each reagent will also have its different side products. Okay. From part A, just now I forgot to mention that with Socyl-2, there is no special condition needed, and the reaction can happen at room temperature. The last one, PCl5, you want to produce butanoyl chloride, so you will need butanoic acid, that is a carboxylic acid with 4 carbon atoms. And the side products when you use PCl5 is hydrogen chloride fume gas and POCl3. Okay, so just make sure that your equations are balanced. The next section of this topic is the reactions of acyl chlorides. Okay, now I noticed that in your notes this one comes first, but I think it's better if we look at the mechanisms first. Okay, because this one will be really straightforward. Once you understand the mechanism, then it's easy to follow the reactions. Okay, so please have a look at please go to page 7 on your notes. Okay, so page 7 on your notes, we will look at a specific reaction of an acyl chloride, which is called hydrolysis. Okay, hydrolysis means water is involved to break a certain bond. Okay, lysis. Now, if you look at the structure of acyl chloride, okay, it looks like it's quite similar to, obviously it's quite similar to carboxylic acid because that's where it is being formed, but it also looks similar to a carbonyl compound. Okay, remember your carbonyl compounds, ketones and aldehydes, okay, where you have a C double bond O, except that in aldehydes and ketones, which is what we call carbonyls, the carbon on the carbonyl, C double bond O, is attached to either hydrogen or an alkyl group. Okay, in the case of an acyl chloride, you have this Cl. Okay, right. Acyl chlorides is actually much more reactive than carboxylic acids. Okay, so carboxylic acid is a relatively unreactive organic molecule. So that's why most of the reaction that started with carboxylic acid is first converted to an acyl chloride first. Okay, and it's easy to convert the carboxylic to an acyl chloride. You just throw in Socyl-2 or PCl5, but of course you need to separate your desired product, which is your acyl chloride, from the other side products of the reaction. Okay, right. So when we look at the structure of the acyl chloride, okay, you have something similar in your notes as well. basically, if you notice that this carbon, okay, this carbon of the carbonyl, if I'm talking about the carbon of the carbonyl, I'm referring to that carbon really, okay? This carbon is attached to two of the highly electronegative atoms or elements, okay? So this carbon is attached to an electronegative oxygen, okay, which is similar to your carbonyl. So oxygen will be slightly negative or partial negative, and the carbon will be slightly positive, okay, or partial positive charge. Now, that's the similarities between an acyl chloride and a carbonyl compound. In acyl chloride, you have an additional electronegative atom or element, which is the chlorine. Okay, now even though chlorine is not considered as the mostly electronegative, but it's quite high as well in the electronegativity series. Okay, so chlorine is again another electronegative atom. So you can imagine this carbon is attached to two most electronegative atoms in the periodic table. Okay, so that means this carbon will have a slightly bigger partial positive or slightly bigger delta positive compared to your carbonyl compounds. Okay, if I draw a carbonyl compound here, let's see. Okay, so C double bond O, and then maybe one side is attached to an alkyl group R and the other side is attached to a H. Okay, now because I have this electronegative oxygen, of course that oxygen develops a slightly negative charge and this carbon will not develop a slightly positive charge. Okay, because there is that oxygen taking away or pulling the bonding electrons closer to itself. In acyl chloride, you don't only have oxygen, but you also have chlorine, okay? So you can imagine that I wouldn't say that that carbon is more positive, but usually we say it is more partial positive, okay? So the delta plus is bigger compared to the delta plus in the carbonyl compound, okay? And if you remember your reaction in the carbonyl compound, it involves a nucleophilic addition reaction, okay? Because nucleophile is attracted, so nucleophile tend to have negative charge and a lone pair, so it attack the slightly positive carbon, okay? Slightly positive is attracted to the negative species, and then one of the carbon oxygen double bond breaks, and then it picks up a hydrogen ion, and you will form what we call a hydroxynitrile. Okay, that's for carbonyl compound. Whether it's aldehyde or ketone, it's the same. Okay, for acyl chloride, it is something similar. Okay, but now you can imagine, as I said, the carbon is a slightly, it has a more partial positive, so it attracts the nucleophile even more. Okay, you don't even need a strong nucleophile. Even water, if you look at water, H2O, water is uncharged, but water has a lone pair because that's the requirement for a nucleophile. As long as you have a lone pair, you can act as a nucleophile, even though you're not charged. Okay, but usually we tend to think of nucleophile must be something that's negative charge, but not necessarily. Okay, in the case of acyl chloride, it can attract the weakest nucleophile, or we say that the reaction happens in a mild condition because that carbon is very, very, how do you say, it attracts the nucleophile more. Okay, so here's an example of a reaction of an acyl chloride with a nucleophile, in which case the nucleophile is water. So we call this reaction a hydrolysis of acyl chlorides. Okay, I believe that you have that space. Example of hydrolysis of acyl chloride, you can copy this down. When ethyl chloride reacts with water, okay, what happens is that you your chlorine in that ethyl chloride has been replaced with OH group. Okay, so when we look at the mechanism, only you will understand why that's the product. Okay, and then you get HCl, same thing. I'll show you how to get HCl in the mechanism later. So for this reaction, you only need water as a reagent and room temperature, no heating whatsoever. Okay. Your observation, well, ethanoic acid would be a colorless liquid. HCl here will be your hydrogen chloride gas. So you will see or observe it as steamy or white fume. Okay, so it's not hydrochloric acid, it's hydrogen chloride gas. Okay, so please copy this down. Okay, while you're copying down, I will talk a little bit on the mechanism. Okay, basically, for carbonyl compounds, aldehydes and ketones, the mechanism is called nucleophilic addition. Okay, you may think that it makes sense. Oh, because you have a double bond, so you can add things to the double bond, which is the C double bond O. But for acyl chloride, the mechanism is called nucleophilic. Okay, it attacks nucleophile, but there is an addition-elimination. Okay, so there are two things. You add things and then you eliminate something. Okay, or another name for this is condensation. Okay, because because water is involved. Right, are you done? Have you copied this down? Okay, right. So condensation, the general definition of condensation is the formation of large molecules involving the loss of a small molecule. Basically, you're combining water and the acyl chloride to form a one molecule, and at the same time, you are releasing a small molecule, which is HCl in this case. Just like your esterification is a condensation reaction, you combine alcohol, carboxylic acid with the loss of water. Okay. And then you'll talk about the ease of hydrolysis later on. Okay, so for your mechanism, we're going to look at the reaction of acyl chloride with water. Okay, so let me just compare this to carbonyl. Okay, for a carbonyl compound, you have it slightly positive, slightly negative on the oxygen. So your nucleophile, I would use an OH minus. Okay, so the lone pair on the nucleophile attacks the slightly positive carbon. Okay, only that carbon. It will not attack other carbon on the alkyl group because this carbon, they don't attract the nucleophile. They're not slightly positive charge. So you can imagine that carbon will form a new bond with oxygen there. Okay, so that means carbon will have 5 bonds. So one of the double bond will have to break. Okay, and you form this. I hope you still remember your AS stuff. O minus. Okay, the reason for that minus charge is because the electrons in that bond goes to the oxygen, and don't forget to attach your OH. Okay, so you can see that the negative charge that was originally in the OH is now on the oxygen. Okay, now I don't want to talk much about the carbonyl because you should already know by now. So then the negatively charged oxygen will pick up hydrogen. Usually it comes from the catalyst. Okay, so lone pair, it's always about the movement of the electrons. Okay, so the lone pair here attacks the H plus, and you form your product COH HR and an OH. Okay, so this is a dihydroxyl. The mechanism that you looked at in AS was a cyanide ion. Okay, so I use a hydroxide ion here. Now we're going to look at the mechanism of acyl chloride. Oh, right, that's right. Thank you. Yeah. Okay. So this was what I was trying to show you. Okay. The mechanism of carbonyl compound, where you form 4 single bonds at the end of the reaction. Okay, or in your product. Now we're going to look at the reaction of an acyl chloride. Okay. So what happens is that, of course, when you draw your acyl chloride, this is your acyl chloride. The carbon is slightly positive, the oxygen slightly negative, and the chlorine is slightly negative. But then you can include the slightly negative charge on the oxygen and the chlorine, but the most important thing is the slightly positive charge on carbon, delta plus on carbon, because that is the one that attracts the electrophile. Okay, so my mechanism has been drawn, so I'm just gonna use my pointer. So one of the lone pair on the oxygen, which is the nucleophile, okay, is donated to the slightly positive carbon. Okay, so you can imagine this carbon will form a new bond with the oxygen. Okay, then of course this carbon will have 5 bonds, so one of the double bond has to break. So that's where you see this arrow. Okay, now next, the formation of the new carbon oxygen bond. Okay, and then your carbon from the carbonyl C double bond O is down here. Okay, I don't like how they draw this, but yeah, it's like that. That oxygen now has a negative charge. Okay, because it receives electrons from one of the double bonds. Okay, now you notice that this oxygen has 1, 2, and then the third bond, which is the new bond form. So that's why that oxygen is positively charged. Okay, also that oxygen has lost one of its lone pair, therefore it becomes positive, right? So in the second step, okay, the difference between carbonyl and acyl chloride is that acyl chloride does not pick up a hydrogen here. Okay, this is the only difference with a carbonyl. Instead of picking up a hydrogen, it reforms the double bond, C double bond O. Okay, so this part. A lone pair from the negatively charged oxygen is reformed, is remaking the bond with carbon. Okay, now so you can imagine if this bond is formed, that carbon in the center would have 5 bonds. Yeah, I hope you can see that. Let me just draw this. Okay, if this was a new bond, right, this carbon will have 1, 2, 3, 4, 5 bonds. So that means another bond has to be broken. Okay, you cannot break carbon-carbon bond. That is a strong bond. You do not want to break this carbon-oxygen bond because it's a new bond that you just formed. Okay, the only bond that can be broken is the carbon-chlorine bond. Halogenoalkane. Carbon-halogen bond is relatively weak. Okay, you can break them easily, right? So what happens? The carbon chlorine bond breaks, the chlorine gets the electrons, therefore Cl becomes Cl minus, which you don't see. This becomes Cl minus, okay? Another part where you don't see is this, okay? That oxygen is positively charged. In order for it to be neutral, okay, because you want a neutral product at the end, is for it to receive electrons. And the only electrons that you can get is from one of the OH bond. Okay, so one of the OH bond breaks and then the electrons go to the oxygen. So that becomes negative and positive neutral. Okay, so that's why you have a neutral COH single bond, right? The C double bond O is being reformed. And so this hydrogen leaves as H plus. Again, something that you don't see. So H plus combined with Cl minus to form HCl. Okay, I hope you can see that. So this is the general mechanism of an addition-elimination reaction. Okay, so why is it an addition? This part is the addition part. You are adding the H2O onto the molecule. The elimination part is this. You are releasing Cl minus from the molecule. Hence, addition-elimination reaction. Okay. Please do not draw this wrong. Okay. So please copy this down. You have a space at the bottom of page 7. Okay. So it explains that water is a nucleophile to attack an acyl chloride molecule as there is a lone pair on the oxygen atom. So you always have to draw the lone pair. The slightly positive carbon on the carbonyl group is attacked by the nucleophile, right? Okay. What else do I want to describe? Okay, that's it. Basically, that's it for the mechanism. I don't like how the mechanism is drawn. I mean, just like the arrangement, but I guess, yeah. Do I have space? I don't have space if I want to redraw this mechanism. It's just so odd to have the C double bond or at the bottom. The reason for this is because when this attack happens, okay, so you can see that an acyl chloride is a planar molecule, okay? So it's a planar molecule, so the nucleophile can attack either from the front side or the back side, okay? That's why you see this this happening. If the nucleophile is attacking on the top side, then the C double bond O goes to the bottom. Okay, but you don't have to worry much about this. Please let me know if you're done, if you have complete. Let me know if you're done copying this down. Done. Nice, Ben. Ang, I haven't heard from you. Oh, Ang replied. Okay. Right. I will not talk about the ease of hydrolysis, but so that's the mechanism of acyl chloride. So now we're going to look at the reaction. So back to page 6. Okay, so page 6 shows the reaction of acyl chlorides. Acyl chlorides can react with alcohols, just like carboxylic acid. Okay, it can react with phenols. Phenols, it acts like a hydrochloric acid. Sorry, it acts like carboxylic acid. Okay. Okay. It can react with ammonia and primary amines, okay, because these are nucleophiles. They have lone pairs. I'll show you later. When acyl chlorides react with alcohols and phenols, esters and HCl would be formed. The esterification process is quicker for acyl chloride than carboxylic acid. It also goes to completion. Now, if you remember esterification from your AS notes, esterification is actually a reversible process. Okay, the forward can happen, the reverse can happen. Now, acyl chloride reacting with alcohol is also a type of esterification process. Okay, because you will form ester bond, C double bond O C. Okay, but this reaction, this esterification reaction, is not reversible. It goes to completion. The equilibrium lies far to the right hand side, far to the product. Okay, so as a matter of fact, if your esterification process is slow, you would change your carboxylic acid to an acyl chloride. Okay. Also, the reaction of acyl chloride with alcohols, you don't need to heat it. You don't need catalysts. Right. So let's have a look. It's also much quicker. Okay. So this is the reaction with alcohol. Okay. More or less similar, right? You will lose the hydrogen from the alcohol and you lose the chlorine from the acyl chloride. Okay. The reason for this is your alcohol is the nucleophile on the oxygen. Okay, so the lone pair on the oxygen will attack that slightly positive carbon. The C double bond O will break, and then you reform the bond, and your Cl goes away. Okay, it looks like that in a single step reaction, but you know that there are two steps in this reaction. Okay, so the ester bond that you're forming is C double bond O C here. Okay, so that is an ester, and the molecule that is being released in this reaction is the HCl. For this reaction, you don't need a catalyst. Now, as you know, esterification of carboxylic acid and alcohol, you need an acid catalyst. Okay, for this reaction, it happens at room temperature. Okay, the reason for that is because acyl chloride is much more reactive than carboxylic acid. That is all. So this works with any alcohol. Okay, alcohol only. Well, it works with phenols as well, right? So same thing. Okay, for phenol, you have this lone pair on the oxygen, so that acts as a nucleophile. For phenol, there is a slightly condition. Okay, condition is required. You need to warm it, and you need an alkali. Okay, the presence of a base. The reason for that is because, as you remember, phenol is an acid. Okay, phenol needs to react with an alkali first so that it creates a phenoxide ion. Okay, so that means if we just look here first, what happens is the base will pick up that H plus. Okay, the alkali will strip off that H plus, and phenol becomes phenoxide, and this is the nucleophile that will attack your carbon. Okay, now phenols do not react with carboxylic acid. Okay, that is something that I forgot to include, but please write it down anywhere. Phenols do not react with carboxylic acid. Okay, but phenols can react with acyl chloride, which is the more reactive version of a carboxylic acid. Okay, same thing, right? If you just imagine the phenoxide, if I draw it, phenoxide, okay, this is your nucleophile. Attack the slightly positive carbon. One of the bond breaks. Oxygen becomes negative. The negative lone pair on oxygen is reforming the double bond. The carbon-chlorine bond breaks. Okay, so that's just the mechanism in one step, but you know that it should be a two-step mechanism. Same thing. This is an ester as well, COOC. It's called an phenyl ethanoate. I won't go into details on naming of the ester. Your side product is HCl. Okay, unlike carboxylic acid and alcohol, your side product is water. Okay. Next, reaction with ammonia. Ammonia is a nucleophile because there is a lone pair on nitrogen. Ugh. What is wrong? Thank you. This, okay, this slide. So if you need to take a screenshot of this, do it now. Okay, so please make sure that phenols do not react with carboxylic acid. From alcohol here, really? Oh, okay, take a screenshot. Well, nothing much, right? Basically, you already know this mechanism, a two-step mechanism. Same thing, same mechanism. It's a two-step mechanism. So this is your phenoxide. This is your nucleophile. And in order to produce this nucleophile, you need to add a base. Okay, you need to warm it. So reaction of acyl chlorides with phenol require a little bit conditions because usually phenols don't even react with carboxylic acid. Okay, so this is the most important thing that you need to write in your notes. Next one is ammonia. Same thing, ammonia, the nitrogen will attack the slightly positive carbon. One of the double bond breaks and then it reforms. Okay, now you can imagine you have 5 bonds on the carbon, so the carbon chlorine bond breaks to release Cl minus. Okay, the hydrogen comes from the ammonia. If you're wondering where the hydrogen is coming from, hydrogen comes from one of the hydrogen in ammonia, and the chlorine comes from this Cl. Okay, so now we don't, the new functional group that we are forming is called an amide. C double bond O N. Okay, so this functional group is called an amide. Some of you, the bio students should know this. Okay, this is an amide bond. So that is what we call an amide. We call this an ethanamide. Okay, ethan because you have 2 carbon and it just ends with an amide. For this, no special condition is needed. It can happen at room temperature. Okay. Next, last one before we go, we have 5 minutes left. Primary amines. Okay, primary amines and ammonia is actually more or less similar. Okay, ammonia is actually a primary amine. Right, so this primary amine is ethylamine. Okay, so you have 2 carbons. Same thing, the lone pair is on the nitrogen. So that's your nucleophile. It attacks the slightly positive carbon. C double bond O breaks. C double bond O reforms. And then the CCl bond is broken. Okay. So that means you are forming an amide bond as well. Again, CON, CON. Now the naming, N-ethyl ethanamide. Okay. So the N is referring to this nitrogen. Right? On that nitrogen, you have an ethyl group. Okay, ethanamide is this ethanamide. So coincidentally, both of them contains 2 carbon. That is what we call a substituted amide and substituted amide. Okay, so don't worry about the naming because the next topic that we're going to do, which is after the holiday, is nitrogen containing compounds. So you will meet a lot more of this and substituted amide. Okay, we call it an N substituted amide. Same thing, the chlorine comes from here. The hydrogen would have come from one of the hydrogen in the ethylamine. Okay, so again, no special condition. It happens at room temperature. Okay, any question or any slide that you want me to go back to? With 3 minutes left, can we go back to phenol? Sure, here. Okay, so this is phenol. Anything that you would like to ask, Ben? Or do you just need to copy things down? Okay, right. So I will just